Welcome back, and the topic of today's video is going to be Eudiometry and gas law stoichiometry. Alright, so first of all, let's define what a Eudiometry experiment actually is. So when we do Eudiometry, what we're doing in the laboratory is we're collecting a gaseous product of a chemical reaction over water. So the over water becomes important, as you're going to see in just a moment. So let's just consider a typical kind of reaction that would give us a gaseous product. So here's a reaction you guys have seen before. We can have two aluminums, that's solid aluminum, reacting with 6 hydrochloric acids to give me 2 units or 2 moles of aluminum chloride in aqueous solution and 3 moles of gaseous hydrogen. So you can see here that the gaseous hydrogen is the product that we're going to be collecting here. So we can set this up in the lab as essentially a limiting reactant kind of problem. So let's just say for grins, we've got half a gram of aluminum that we've weighed out. And we're going to allow that to react with an excess amount of hydrochloric acid. So because of this, we know that the aluminum is going to be our limiting reactant. Okay, so in other words, when we use up all of the aluminum, the reaction is going to end. So how do we actually set the reaction up in such a way that we can collect the gaseous product as the reaction proceeds? So what we do is we use a simple instrument called a Eudiometer. Now a Eudiometer, which you will use in the lab, is essentially a closed-ended tube. Sometimes it actually looks like a burette, and we can just close the stopcock at the top of it to trap the gas. Or we can usually just think of a Eudiometer as being a closed-ended long tube. And what we're going to do is we're going to actually take our piece of aluminum and we're going to suspend that at the bottom of the Eudiometer. Now, before we do that, we're going to fill the Eudiometer with a solution of hydrochloric acid so that we know we have enough of it that it will remain in excess at the end of the reaction. So what we do is we introduce the aluminum into this end of the Eudiometer, we flip the whole thing over, we suspend it in essentially a beaker or container of water here. Now what happens is the hydrochloric acid will work its way down through the Eudiometer until it reaches the aluminum. Once the hydrochloric acid in the Eudiometer reaches the aluminum, a reaction starts to form. One of the products of the reaction is the gaseous hydrogen. So what that means is that as the aluminum gets used up, we're going to see little bubbles of hydrogen bubbling up to the top of the Eudiometer where they will collect. So the reaction will proceed this way until all of the aluminum is used up. So at the end of the reaction, what we're going to see is a situation that looks like this. We're going to end up having a water column here, and at the top of the Eudiometer, I'm going to have a void here where there isn't any liquid. And what's going to occupy that void is going to be a mixture of 2 gaseous components. One of those gaseous components, of course, will be the hydrogen gas, which was the product of the reaction. And the other gas that inhabits that void is actually going to be water vapor. Now this is where the collection over water becomes important. Because we're actually collecting the gas over an aqueous environment, the water itself at a given temperature is going to have a vapor pressure associated with it. So what that means is there's going to be some water vapor in there as well. So that means that the total pressure inside of the top of the Eudiometer, based on the gases there, according to Dalton's law of partial pressures, has to be the sum of the partial pressure of the hydrogen gas and the partial pressure of the water vapor that's there, because we are collecting the gas over water. And we're going to state that right here. Now, here's the other thing that we have to think about. Keep in mind that this liquid level is not moving. So we have a system at equilibrium here. So what's happening is, remember, based on the atmospheric pressures we learned early on in this chapter, we're forcing that water column up. However, we actually have trapped gas in the top of this thing that's forcing the water column back down. So since the level of the meniscus is not changing, we know that the atmospheric pressure forcing the gas, or rather the water column up, that atmospheric pressure has to be equal to the partial pressures of the 2 gases that are opposing it. Okay, so this is essentially a way of expressing Dalton's law of partial pressures. So if I know the atmospheric pressure and I know the vapor pressure of water at a given temperature, I ought to be able to back calculate the pressure of the hydrogen gas. All right, so next thing we're going to do is take a look at a quick example showing us how we'll use these techniques. All right, folks, so let's take a look at a simple example here. This is number 27 on your handout. What we've got here is a 1.65 gram sample of solid aluminum that we're going to allow to react with excess hydrochloric acid using the reaction that we just showed you. We're going to collect the hydrogen gas, which is a product, over water at a temperature of 25 degrees Celsius and at a barometric pressure of 744 millimeters of mercury. So this is the atmospheric pressure. So the question then is, what is the volume of the wet gas that we collect? When I mean wet gas, what I'm talking about is the combined hydrogen and water vapor that we actually collect in the top of the eudiometer. Now, we also know that the vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury. So we're going to start here by using Dalton's law of partial pressures, which we just left off with a moment ago. I know that the atmospheric pressure, which is bearing downward on the water column, has to be opposed by the total pressure of what I have in the eudiometer, which is going to be the partial pressure of the hydrogen gas plus the partial pressure of the water vapor. Now what I'm interested in, since we're putting this in terms of hydrogen gas, because that's going to be the product that we want, I want to know what the pressure of the hydrogen gas by itself is going to be. So I'm just going to rearrange this equation so that I know that the pressure of the hydrogen is equal to the atmospheric pressure minus the vapor pressure of water. So I can do the math here and figure that out. 744 millimeters of mercury is my atmospheric pressure, minus 23.8 millimeters of mercury, which is the vapor pressure of the water at that temperature. And when I subtract one from the other, I get 720.2 millimeters of mercury. Now ultimately, I'm going to use the ideal gas equation, so I want to convert that to atmospheres. Now again, this is the partial pressure of the hydrogen gas by itself. Do my conversion, and I get 0.9476 atmospheres of pressure due to the hydrogen gas. Now, keep in mind that I've got my balanced chemical reaction equation here, and ultimately what I'm looking for is a volume. All right, so I need to have a value of N for the hydrogen. I need the number of moles of hydrogen gas that I'm going to make. Now, I can take advantage of the fact that this is a limiting reactant calculation. I know that the HCl is in excess. I know I'm starting out with 1.65 grams of aluminum. I got a balanced chemical reaction equation. So what that means is I can employ a mole bridge that takes me from aluminum over to hydrogen. All right? So that's where we're going to pick this up. So starting out with our mole bridge, we can take our 1.65 grams of aluminum here, and I can convert that to moles of aluminum. And then using our mole bridge here, I can relate moles of aluminum back to moles of hydrogen. I know that for every 3 moles of hydrogen that I've got, I'm going to be using up 2 moles of aluminum. All right, so based on this limiting reactant calculation here, we're going to get a value of 0.091728. moles now of hydrogen gas produced in the reaction. All right, so again, that's going to be good to 3 sig figs there. So now we're in a position where we've got everything we need to employ the ideal gas equation. Okay, so we know that that is PV equals to N times R times T. In this case, I'm after volume, so I'm going to solve for volume. So volume is equal to N times R times T divided by P. All right, so now let's get everything into the equation in the correct units here. So volume is going to equal to my number of moles of hydrogen gas that I've made, which is the 0.091728 times R times my temperature. Now my temperature is 25 degrees. You add 273 to that, you get 298 Kelvin. All right, all of that is going to be divided by the pressure of the hydrogen gas. All right, we have the pressure of the hydrogen gas. We figured it out over here, 0.9476 atmospheres. Okay, if everything works out, we should actually end up with a volume unit of liters here. So it looks like moles will cancel with moles, kelvins with kelvins, and it looks like atmospheres cancel, leaving me liters in the top, and that's exactly what I want. So now when I do the math out here, my volume turns out to be 2.37 liters. And I believe we wanted this in milliliters of gas. I think that's ultimately what the problem asked for. We can go ahead and make that conversion if we want to. I didn't specify it there, but I think that's what it's looking for. So for every 1 liter, I've got 1,000 milliliters. And that means this is going to be 2.37 times 10 to the third milliliters of wet gas collected. So that's a typical kind of eudiometry problem. We'll work on a few more of these in class when I see you next. Have a good one.